Does anybody have homework questions? Before we begin our review, I wanted to address the feedback that you gave me last week. So if you were here last week, I think it was Monday, I asked for feedback on how class was going for you. And I really appreciated hearing how some of you are feeling and also seeing the enthusiasm that some of you have for learning something new and a different kind of math than maybe you saw in earlier classes. I did want to address some of your concerns though. So somebody said they would like more examples. Just raise your hand and let me know, and I'll be glad to give another example. Or if that feels odd to you, write a note to yourself and email me, and I can start the next class with another example. Somebody said it was too easy, so I see your grades. So if you feel like it's too easy, be happy, okay? Because some of people are struggling. There's no prerequisite for this class, so we have people who just really feel uncomfortable with math and struggle with it. So if you feel like it's too easy, then I'm glad for you. I'm really glad for you. Some of you were asking about your grade and concerned about it, so I wanted to show you that I did post a grade calculator on D2L. So I don't know if we talked about that before. It's on content, and you would open it on a computer where you would have a spreadsheet available. So here it is. You can put in what you had gotten on your first quiz. So maybe you didn't get off to a good start and you're wondering how that's going to affect your grade. Well, you can put in other prospective quizzes and homework and see how that does. Okay, so you can put in other grades here. I'll just put 85s. And this person could still get a very solid C with 85s for the rest. So you can experiment there. Don't type in the grade column or you'll wipe the grade out, of course, and then the formula won't work. If you ever want to talk to me one-on-one about your grade, I'm happy to do that also. So somebody said they had ungraded material in the D2L Dropbox. I do finish each week before I leave Friday afternoon. So if you have ungraded material that's older than the week before, then it's probably that you entered it late, because I don't take late class activities, so that could be what happened, or something else happened. So if that's the case where something else happened and it's not that you entered it in late, but it's not recorded, please email me, okay, so that I know what's going on. I don't go back. Dropbox for D2L doesn't have a nice way for me to go back a second time and say, okay, what did I miss or anything like that. So I go through it once and that's it. So go ahead and email me if something doesn't work. Something's not shown as a grade. Also, a couple of people really didn't like it that I didn't have the Dropboxes dated. And that's because our class doesn't always get done when like I'd like it to. Sometimes we go slower or faster. Well, at any rate, I thought, fine, if it's that important to you, I'll put some dates out there. So all the Dropboxes now have dates. I might move them farther away, but I won't move them earlier. So if that helps you with your scheduling, that's great. I'm glad it will help you. Somebody would like a printed text. Some of my students do use printed text. They go to Wiley and choose the Read Study Practice. Pick a section, so I'll just pick this one. And then right here, pick the printer version, and this prints off this section. So you can print off various sections. I personally would rather do that myself as well. And of course, you could purchase a hardcover book, but that's probably very expensive. And I would guess it's at least $100 for that text separate. So if that was your comments to me, and I appreciate the feedback, if you ever have comments you want to leave, feel free to let me know. You don't have to wait till I ask for comments. I did want to look at a couple of things together on the review. So one of the things on the review, let me get that up on the screen. One of the things on the review in chapter 3 3.4, answer the 4 questions at the bottom of page 374. I thought we'd look at that together. I changed it from saying page 174 to saying the first page of 3.4, so let's look at that together. We were looking at infinity there. So we were looking at different sizes of infinity, and we'll just review that a little bit. Let me hit the lights so that it comes in more clearly. I guess it does come in more clearly. As good as it's going to get. Oh, I know. It's the first sunny day we've had in a month. That's why it feels so bright in here. Isn't that nice? Wow. Okay. If the light bothers you, feel free to lower the blinds, okay? Anyway, the first 4 questions are at the bottom of this first page. So right here, questions 1 through 4. I'll make it a little bigger. So on your quiz, I'll pick a couple of these, and they won't be labeled 1 through 4, so make sure you understand the questions themselves. And I'll transpose the first 2 words. So statement 1, instead of a question, we'll say there is, and then you'll have to pick true, false, or unprovable. Okay, so true, false, or unprovable. So the first one, there is an infinity that is greater than the infinity of the set of natural numbers, yet less than the larger infinity of the set of real numbers. So the 2 sizes of infinity we looked at 3.3. The size of infinity that's the same as the size of the natural numbers, so that matches the numbers 1, 2, 3, 4, etc. And then the size of infinity that's the size of the real numbers. So that's all the numbers on the number line. So those were 2 sizes of infinity that we looked at in 3.3. And in this 3.4, we have the statement, or it's a question now, but it will be a statement. There is an infinity that is greater than the infinity of the set of natural numbers, yet less than the larger infinity of the set of real numbers. Does anyone remember, is that true, false, or unprovable? Is there an infinity in between there? We have these 2 sizes, the set of natural number sizes of infinity and the larger infinity of the real numbers. Anybody remember if there's a size of infinity in between that or not? It was actually, that was unprovable. That was called the continuum hypothesis, and it can't be proven that there is a set in between, and it cannot be proven that there is not a set in between, which is really a weird thing to happen in mathematics. So number 1 was unprovable. I'll write that on my review sheet, but you'll have to see that in a minute since I have the other screen up. Okay, number 2. There is an infinity greater than the infinity of the set of real numbers. Was that true, false, or unprovable? Is there an infinity larger than the infinity of the real numbers? So we just talked about this. We didn't read section 3.4 in detail. Anybody remember what I told you? Yes, there is. Okay, so that one's true. There is an infinity larger than the infinity that's the size of the real numbers. So number 2 is true. Okay, so now you know there's at least 3 sizes of infinity. Natural numbers, real numbers, and one bigger than the real numbers. But number 3, there are infinitely many different sizes of infinity. Anyone remember that one? Yeah, true. That was true. There are infinitely many sizes of infinity. And 4, there is a largest infinity, one that encompasses all others. True, false, or unprovable? False. Yeah, that's false. So make sure you understand those so that you can answer, because I'll pick a couple of them to put on your quiz. Okay. The other thing I wanted to look at in this section was also about infinity. It was section 3.3. So in 3.3, I actually answered some of the mindscapes and put those on D2L content. So on D2L content, you'll want to practice under other supplemental material. And speaking of practice, you can go practice with Jake at 2 o'clock in the library on the second floor, right? So he'll be practicing and preparing for the quiz for study group. Okay, but if you can't go see him and you want to practice on your own, under other supplemental material, there's some problem answers to go with Cantor's diagonalization proof. So 3.3. So the mindscapes that were on Wiley Plus were not the same as the kind that were in the text, and were not the same as the kind we did in class. So I wanted you to have some examples like you'd see on the quiz. And so these are the answers to those. So these answers go with the problems in Wiley Plus in the textbook. So just go to section 3.3 and page down. Why am I not paging down?
There's a smaller scroll bar next to the large one.
Oh, thank you very much. So at the end of 3.3, there's the mindscapes, and I have the questions on D12 for numbers 8, 9, and 12. So you can do those there. We'll look at 12 a little bit together. So remember from class, we had this column of numbers that were supposed to be paired with the natural numbers. And we were finding M, the missing number. We were looking at proving that the natural numbers and the real numbers are not the same size because the real numbers cannot be listed. So to do that, we've proposed a list. We said, okay, well, suppose this is the list. And then we constructed M, the missing number that's not on the list. So that started out 0 point something. And then after the 0, we filled in a number based on the proposed list. Does anybody remember what the first digit would be, the first decimal place? 2. Good. And why is the first decimal 2? Good. It is 2. Does anybody remember why? So we were using 2s as our default and 4s as our backup. And we picked 2s if the first decimal place was not a 2. And we picked 4s if that decimal place was a 2. So we're trying to build a number that we are positive is not on the list. And we do that by making sure we don't match the first decimal place. So put a 2 in the first decimal place. Second decimal place, with the second number, we also put a 2. Third decimal place, we put a 2, because that's not a 2. Fourth decimal place is a 2. So the fourth decimal place in the fourth list is a 2, so we pick a 4. So we're sure now we don't match row number 4, because the fourth decimal place is different. So this is why we were playing dodgeball. We always miss the number on the diagonal, so we know we're making a number that's not on the list at all. And then the fifth decimal place and the fifth number is a 5, so we can go back to our default 2. So we always use the 2 as our default, unless that decimal place was a 2, and then we use a 4. So you get some practice with that in problems 8 and 9. In problems 8 and 9, you'll have to use the list that's up a bit. So you can practice problems 8 and 9 using a list that's up in the textbook. A little more, a little further. A little further, there's the list. Okay, so construct numbers to practice Power Mindscapes 8 and 9 using this list. Does anybody have any questions? And then check your answers with D12. So those are the ones I wanted to go over with together, and then the rest I'd like you to start on in groups, and then we'll do that for a few minutes, maybe like 5 minutes, and after that we'll work together again to get your answers recorded. So I'm going to split you up into 9 groups. We'll look at the review sheet together then. So online students, you can pick out a section to work on, and then we'll all talk together. Okay, so how about one group? Two groups. And then, how about formation? You four, you can work together. So that'd be 5. And then each row can be a group over here. Okay? So let me assign you one, not a section. So you can do 3.2. And you just can do 3.3. And you can do 4.1, and I'll be looking for recruits, so hopefully you have compiled recruits module, okay? And this group can do 4.2. And this group can do 4.3, please. And this group is 4.4.
So we take it. That's what we do. Yes. And then, I don't know if it comes with
Well, let's go ahead and work together. So first some generalities about the quiz. It's Wednesday, 55 minutes. If for some reason you don't want to take it now, you can take it at 6:30 a.m. or 4:30 p.m. It is 3:26. Online students, if you want to take it with this class, you can. It looks like there's 4 or 5 places. Just email me for the room. All right, so there's about 19 questions. Bring your 3x5 card to your quiz. You can, if you want, bring your Pythagorean right triangles and squares. That's kind of optional. Some students just put the proof on their card. Definitely bring a compass. I can tell when you don't use a compass on those drawings, and you will not get full credit if you do not. Okay. If you're here with me and you borrow my compass, that's fine. But everybody else has to bring their own compass. A ruler, because one of the questions will ask you to confirm your measurements of the rectangle you make. So don't forget these. The platonic solids, tape, and scissors are optional. Sometimes students like to have those to confirm what they've written on their 3x5 card, and sometimes their students are satisfied with what their card says. Yes, you can borrow from me. Yeah. Okay, so some specifics now. Section 3.2, the natural numbers and the rational numbers were those fractions. 3.2, were those the same cardinality or different cardinalities? Same. They are the same cardinalities. And then in Mindscapes 6 through 10, you had some practice problems to show that sets have the same cardinality. Did you happen to have an example of one of those?
Over 6, it was evens and odds.
Evens and odds.
Do they have the same cardinality? And they do. I mean, you can show that by doing that.
Good. evens and odds, and they do, and you show it by listing them, right? And then showing little arrows going between. So there's a number of different sets there that you can show have the same cardinality, and you show the same cardinality by listing them and doing the double arrow. Not missing any and not counting any twice. Okay, great. Then in 3.3, the natural numbers again. And this time the real numbers. So those are all numbers on the number line. So those are fractions, square roots, cubed roots, pi, whole numbers, decimals, all the numbers. 3.3, what did you decide? Same cardinality or different? Yeah. Okay, so no, they do not have the same cardinality. In fact, we don't know if there's a cardinality in between those two. That was the question we talked about in 3.4. We don't know is there a cardinality in between those, the natural numbers and the real numbers. So these mindscapes we looked at, and the answers are on D12 for you to check. Test, quiz yourself on those, okay? We looked at 3.4, and that brings us to 4.1. So I'm going to see, yes?
There's a question about the natural real numbers. We did that spiral once.
That was this one.
That was that?
Yeah.
Okay.
Yep, and that's how they turned out to have the same ones. The natural numbers and the real numbers were where we found the missing number that wasn't on the list. Like we couldn't list them because we tried, and oh my, look, there's a missing number, no matter how much we try.
Okay.
I'm going to gather up your proofs so that they can you have one of each. Oh, you wrote, I thought you might have it in your notes. Oh, so you wrote it. Yeah, that's sufficient. We'll just show it. You have all of that. Okay, thank you. So once again, the part that you have to do that isn't just answering yes or no, but you have to show something is worth more points. So these proofs would be worth more points. Remember, you only need to know one proof, and I refer you back to those videos where we did all three. So one proof had 2 diagrams plus quite a bit of algebra. One proof just had 1 diagram, but it had a little more algebra to work out. And then one proof had no algebra, but you had to have the diagrams, showing the c squared equals a squared plus b squared, made up of the same parts. Now, all of these proofs should have the triangles labeled with A, B's, and C's, and the square labeled with A minus B and A minus B. So this one, add one more thing. Add A minus B and A minus B, okay? And then you're set. So pick out the proof of those 3 that you like best. You don't have to know all 3. Hopefully one of them clicked with you, and you can remember it pretty well from what you write on the 3x5 card. Also in that section, you'll have to use the Pythagorean theorem, so I'll give you 2 sides of a triangle and you find the third. So make sure you know how to do that. Yes?
Is it going to be like life size, like with trace the triangles we have, or is it going to just be like a sketch? Like, my problem was during the notes that it wasn't too straight, so it was, you got the point that they're supposed to put together, but they didn't work. For the Pythagorean theorem.
For the proving part?
Yeah, the sketches didn't always fit.
Oh, okay, so you're drawing the sketch yourself. So it's up to you how big you want to make it. I'll provide about a half a sheet of graph paper in size.
Is it fine if it's not completely like?
It doesn't have to be to scale,
It's
no.
just the listing, the information.
Right, the information labeling A, B, and C correctly shows that even though you didn't draw it quite to scale, the A is supposed to match the A. Okay, so it does not have to be to scale. Did that answer your question?
Yeah.
Okay. Okay, so 4.2, I'm going to give you several shapes. In fact, I'll give you the shapes we started that class with and ask you which are polygonal closed curves. Okay, so 4.2. Which of those is a polygonal closed curve? I'll label them A, B, C, and D. Is that your group?
Yeah.
Okay. You're like, wow, this is a pop question. We thought we had to figure it out, and now you give me a. Okay, so confer, and then tell me what you think.
Isn't it just D?
Good. It is just D. So just D is the polygonal closed curve. A polygonal closed curve, remember, is straight lines connecting end to end until they are closed up again. There's not any extra straight lines like this one has. There's not an opening like this one has. And there's not another inside. All the lines connect one to another. And you can trace from beginning to end without picking up your pencil. So, did you read what the art gallery theorem says?
Yes.
Okay. What is the art gallery? It's kind of long, actually.
Yes, so I have in my notes. Suppose we have a polygonal closed curve on the plane with V vertices. Then there are V over 3 vertices from which it is possible to view every point on the interior of the curve. If V over 3 is not an integer, then the largest number of vertices we need is what we need to, like the number of guards.
Good. Good. So we're finding the number of guards in the art gallery, and you said it had to be V over 3, where the number of V is the vertices. And if that doesn't come out to an integer, then it's the whole number that's smaller. So let's count the vertices on this one. In fact, we'll practice on this one. This is supposed to be a straight curve, okay, right there, a straight line. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices. So that would say V over 3, or 3 places where the guard needs to be placed. Now on the quiz, what I'll ask you to do is triangulate this and then label the triangles properly on their corners, red, white, and blue. So let's practice that on this one, and there's more you can practice online. There's a sheet with 4 polygonal closed curves online that you can practice with. So let's triangulate these. It's nice to do it with a pencil. I neglected to bring a pencil, so I'm going to use a pen. So it's always vertice to vertice. And when you connect 2 vertices, if it doesn't make a triangle, then continue connecting. So always connect vertice to vertice, and in such a way that your lines that you're connecting to make triangles don't cross each other. So I'll just do that this way. Now, once you do that, you have to label red, white, and blue. So pick one of the triangles to label red, white, and blue. As you do that, you'll have labeled one line from another adjacent triangle. So I labeled red and blue here. That means this triangle's other corner has to be white. So you have to be careful and follow through triangle by triangle so that you don't get to the end and you're like, wait, why does this triangle have 2 whites and a blue? If I switch this white to red, then this one has 2 reds. Okay, so you don't want that to happen. So start with one, and that will tell another line what color it needs to be, and that dictates the third point. Okay, so now I have red and blue, so this corner has to be white. Now I have blue and white, so this has to be red. Red and white, so this has to be blue. Red and white here, so this has to be blue. Red and blue, so this is white. Okay, so once you've labeled all of those, I'll ask you to write down red, white, and blue. There are more than one way to triangulate these, and there are more than one way to write the red, white, and blue down, which is why I'm asking you to label how many vertices there are and how many red, white, and blue there are so that it's easier for me to check. Okay, so on here I ended up with three reds, 4 whites, 2 blues. That's not right. I must have miscounted. 1, 2.
There was 10 vertices.
10 vertices. Okay, thank you. And that's another thing. That's a nice check, right? So we have 10 over 3. 10 over 3 is 3.3. So you need the 3. You need the whole number, the 3 cards. Okay, so 3 blues. So since we have 3 reds and 3 blues, you can pick either the red corners or the blue corners to put your cameras on, and that's where you put the circles. So I'll put circles on reds. So red, 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 and that's where the security guards should stand. So we cover this whole gallery with 3 security guards, and it's possible if you just stare at it, you could do it with less, but we want to use the art gallery theorem for this so that I know you understand how the art gallery theorem goes. So please try and follow the steps of the art gallery theorem. Even if you think, wait a minute, if I had a guard standing right here, he could see everything this guard stands, so I don't need that guard. Just do the theorem, okay? In real life, you can narrow it down after you use the theorem. Any questions on that? Okay, so that brings us to 4.3. So 4.3 group, can I have your 2 golden rectangles? Okay, do you have? Okay. Does anyone else in your group have this with the whole thing? Okay, then I'll just show her. So the first golden rectangle starts with a square, and then the M goes in the middle of the square, and here's where you take your compass and measure to the upper right corner, and use that compass then to draw C. So you must not have had a compass that day, right? So when you have a compass, it'll come out right here, and then you draw your vertical line there. And then we have the other way to draw the golden rectangle using the Fibonacci sequence. So you'd write down the Fibonacci sequence: 1, 1, 2, 3, 5, 8. And we do a 1 by 1, 1 by 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8. And as you do that, you're doing the counterclockwise direction as you build them on each other. And then you can put the spiral through those corners. So once you do that, take a ruler and measure. Your problem will ask you to take a ruler and measure and confirm that you do get phi. What was phi about? Yeah, about 1.6. So if you're a little, if you're at 1.5 or 1.7 with our measuring devices that we're using, that's great. So make sure you have a compass that day, because like I said, I'll take off points if you're not using a compass that day. So bring a compass. So that brings us to 4.4, where we were looking at symmetry and tiling the plane. Do you have some diagrams? So first you had to demonstrate symmetry of scale or rigid symmetry. So I'll be asking you which kinds of symmetry a particular drawing that I give you has. So we should know what is rigid symmetry and what is symmetry of scale. What is rigid symmetry? Did you have that definition, either of you?
Symmetry in a plane. Symmetry? I wrote it wrong, but is a motion of the plane that preserves the pattern and does not change structure otherwise dictated.
Okay. So symmetry in the motion of the plane that preserves the pattern. So we demonstrated that with transparencies. So if we put a transparency of this over top of it and slit it left or up or down, would it preserve the pattern? Do these triangles have symmetry, rigid symmetry? Well, you'd have to slide it down quite a bit, but not too. I mean, you take this triangle and slide it down to this triangle, and that would drag these other ones down, right? Okay, so these triangles do have symmetry, rigid symmetry. Otherwise, you could think of rotating a transparency on top as well, and that would also show you that you have rigid symmetry in that fashion. Or you could flip it. So any way you can move that transparency and keep the same pattern is going to be rigid symmetry. Well, what was symmetry of scale then?
Pattern of the plane that has symmetry of scale or scale of the tiles that make up the pattern can be grouped into super tiles.
Okay, so you can build super tiles that are the same proportion. And that if you were to shrink down those super tiles, you would have the same pattern that you started with. So how many super tiles would you put together here? How many tiles would you put together to make a super tile here? 4. Yeah. So here, if you took this one, you could say I'm going to copy that by making this one, which has 4 little tiles, and makes one large tile that is the exact same shape, just larger. Okay, so that's symmetry of scale. So this particular pattern has rigid symmetry and symmetry of scale. So I'll have a pattern for everybody's quiz, and you'll have to pick, does it have no symmetry? Does it have rigid symmetry? Does it have symmetry of scale? Does it have more than one of those? And you'll have to pick. So then there was the pinwheel tiles. So there'll be a graph which you can download on D2L, this same picture, and you'll have to find your own super tile there, and you'll have to find a super tile. So the super tile has 5 tiles, and then the super tile has 25 tiles. So you'll have to be able to find one there. And then I'll ask you to outline all 5. So I'm going to draw in here this 1, 2, 3, 4, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So there should be 25 tiles when you're all done, and they should be in groups of 5 making the super tile. Now, this was an interesting pattern because it has what kind of symmetry? What kind of symmetry does this have? Yeah, this has symmetry of scale, right? Because you can build the super tiles, but it had no rigid symmetry, and that's unusual to have symmetry of scale with no rigid symmetry. Oh, I was going to say, online students write dark here. Because you're just getting scanned and sent to me if you're an online student, and I need to be able to see it come through the scan properly. I don't think did I assign anyone 4.5?
Yeah.
Okay. Can you read me the rows across in just a minute? I'm just gonna double check. Okay. So please read me the tetrahedrons row.
4, 6, 4, 3, 3.
Okay.
8, 12, 6, 3, 4.
Okay.
6, 12, 8, 4, 3.
Okay.
20, 30, 12, 3, 5.
Okay.
12, 30, 25, 30.
Okay. Thank you. So you can bring that on your 3x5 card. I'll ask you separate columns. So everybody's quiz will have different columns I'm asking about. Make sure you don't get your columns mixed up or you'll lose points. I won't reorder the platonic solids, so it'll go smallest number of faces to largest number of faces because that just gets confusing otherwise. But do keep your columns straight. What about duality? Someone else in your group? What's dual? What's dual with what?
The cube, the cube and the octave.
Yes.
And then the dodecagon and the
Yep, the cube and the octahedron and the dodecahedron and icosahedron. Good. And what about the tetrahedron? What's that dual with? That's dual with itself. We did not do 4.7. We'll be doing that Friday. And that brings us to 5.2. So your group had 5.2 as well, right? What is this? How many sides does a Mobius band have? Somebody else in your group can answer, right?
That's
One side, good. And how many edges? One, good. What is this diagram?
cylinder.
Cylinder, yes, a plane loop or cylinder. There was one more cylinder on there. Did you find it?
The one on the bottom on the right hand side.
Good. So both of these are cylinders. Doesn't matter if you put the long sides together or the short sides, they're still cylinders.
Do you want us to put cylinder and plane loop? Or
No, you can put cylinder or plane loop.
Okay.
What was this one? So the Mobius band had a half twist, and that's why one arrow points down and one arrow points up, because you put a twist in so that the arrows match when you connect. And what was this one?
Donut.
This is a donut or a torus. Either word is fine. So here you connect the long sides together and make a tube, and then you connect the short sides together. So the double arrows go together to make a tube, and then when you take that tube and put these arrows together, you've made a donut. And what was this last one that was kind of hard to make?
Line.
Yeah, that was a Klein bottle. So that one's almost like a donut, but there's a twist in it, and you can only form that twist in its purest form in the fourth dimension. But we worked hard with paper and got a three-dimensional approximation. Okay, in 6.2, what is the Euler characteristic of connected graphs? What did you decide? Good. V minus E plus F is 2. And you hopefully put dots on the vertices, beginning and end, and where they're crossing. How many vertices were there then? 5? Good. Whoops. How many edges? 7? And how many faces? 4. Don't forget the outside counts as a face. So let's just check. So once you do this, check. I'm always surprised how many quizzes I get where this doesn't come out to 2. I'm like, what? You know, the check is pretty easy. Take V minus E plus F. You should get 2. So you'll also see some problems in this section where you're given 2 of the quantities, either vertices, edges, or faces, and you have to find the third one. So you have to do a little algebra there. Yes?
In 4.4, we skipped over the be able to construct a golden rectangle from a given rectangle. How do we do that again?
Thank you for pointing that out. 4.4. It's supposed to say triangle, and I accidentally wrote rectangle. The proportions of a golden triangle were 1, 2, square root of 5. And the way that you made that, you take your lined paper or your graph paper, and you make 1 unit tall, and then take another piece of lined paper or graph paper. Well, you can do this with a ruler too, and just do 1 inch and 2 inches. So whichever units you're using, inch and 2 inches, centimeter and 2 centimeters, 1 line and 2 lines. And then when you connect, you get a golden rectangle. I might have asked you to make another golden rectangle from that, so then you would put one this way, and another one on top, and the tip. Whoops, I did it wrong. Here, use your pinwheel to look at. So you should have this T thing going on, and I did it backwards. So you have this T thing, so make a T with another one on top, and then your tip would go this way, and then you'd have another one off the back here. Okay. So you can copy that from your picture if you need to. Any other questions?
Are you gonna give us graph paper for the?
There'll be graph paper in lots of different places. Any other questions? Yes. Wednesday. Good thing you asked. Wednesday. Any other questions? Okay. 4.7 is skipped.
Oh, alright.
Till Wednesday, Friday. Well, thank you all for contributing. I'll see you on Wednesday. Please feel free to email me any other questions you have.